A rock from another star system just buzzed Mars. And it's glowing green. I'm Mark, astrophysicist, and this changes everything. On October 3rd, 2025, interstellar comet 3I/Atlas made its closest approach to Mars, just 2.1 million kilometers away. That's closer than Earth ever gets to Jupiter. Martian orbiters captured it in stunning, high-resolution detail. What they found? Bizarre chemistry. A coma shimmering emerald from diatomic carbon, nickel levels off the charts, and a trajectory screaming, "I don't belong here." This isn't just another space rock. It's a messenger from beyond our solar cradle. In the next hour, you'll discover how this object was found by a telescope system designed to spot Earth killers, why its green glow has scientists whispering about prebiotic chemistry, how its path proves it was flung from another star system millions of years ago, and why some researchers are already calling it the most important interstellar visitor since Oumuamua. This isn't just astronomy. It's a story about where we came from, what's out there, and whether the universe is seeding life across the void. Stick with me. You're about to see the cosmos in a whole new light. Picture this. It's a quiet Tuesday morning at the Atlas Observatory in Hawaii. The twin 0.5-meter telescopes, part of NASA's planetary defense network, are scanning the sky, not for aliens, not for glory, but for asteroids that might one day hit Earth. Routine, automated, boring even. Then, ping, an alert flashes. Object moving too fast, too straight, too wrong. Initial orbit calculations show an eccentricity of 1.0037, not 0.99, not 1.00, 1.0037. That number? That's the fingerprint of interstellar origin. Anything above 1 means it's not bound to our sun. It's just passing through, like a cosmic hitchhiker with no return ticket. You're probably wondering, wait, didn't we already have 2 of these? Yes. 1I/Oumuamua in 2017, mysterious, cigar-shaped, accelerating oddly, and 2I/Borisov in 2019, more comet-like but still alien. But 3I/Atlas? This one's different. For starters, it arrived on our doorstep. While Oumuamua was spotted after perihelion, already fading, and Borisov was distant, 3I/Atlas gave us a front-row seat. Thanks to its Mars flyby, we didn't just get blurry pixels, we got spectra, we got thermal maps, we got composition. And here's what shocked everyone: the green. Not a pale hint, not a subtle tint, a vivid, luminous emerald halo surrounding the nucleus, so bright it was visible in amateur telescopes across the southern hemisphere. That green? It's not magic. It's chemistry, specifically diatomic carbon, C2, breaking apart under solar UV radiation. We see it in comets from our own solar system, sure, but never this intense, never this structured. The Mars Reconnaissance Orbiter's CRISM instrument measured C2 emissions 3 times stronger than in any known Oort cloud comet. Why? That's the first mystery. But wait, it gets weirder. When ESA's Trace Gas Orbiter pointed its NOMAD spectrometer at the coma, it didn't just see carbon, it saw nickel. Not iron, not sodium, nickel vapor in gaseous form, streaming from the nucleus at temperatures far too low for typical sublimation. In our solar system, nickel only appears in cometary tails when the object gets scorchingly close to the sun, like within Mercury's orbit. But 3I/Atlas was still beyond Mars, over 1.5 AU out. How is nickel boiling off in the cold dark? One team at the University of Liège suggests it's bound in an exotic volatile-rich matrix, maybe something like nickel carbonyl, which decomposes at just minus 20 degrees C. If true, that implies chemistry we've never seen in nature, chemistry that might only form around certain types of stars. I still get chills thinking about it. We've spent decades wondering if interstellar objects carry the building blocks of life. Now, one shows up with a green glow and alien metals and it's practically knocking on Mars's door. Let me take you back to September 12, 2025. That's when Atlas first logged the object, designated A/2025S3 at the time, as a faint, fast-moving dot in the constellation Cetus. Within 48 hours, the Minor Planet Center flagged it as highly hyperbolic. By day 3, telescopes worldwide were locked on. The Hubble Space Telescope swung around. So did the Very Large Telescope in Chile. But the real gold came from Mars' orbit. Think of it like this. Imagine you're trying to study a firefly flying past your window at night. From your porch, you see a blur. But if your neighbor has a high-speed camera on their roof, pointed right at it, you get slow-motion detail. That's Mars. While Earth-based scopes struggled with atmospheric distortion, MRO and TGO had a crystal-clear, close-range view. And what they saw defied expectations. The nucleus? Only 800 meters across. Smaller than Borisov, much smaller than Oumuamua's estimated size. But it's spinning. Fast. Every 4.2 hours, with a slight wobble suggesting it's not a solid chunk, but a rubble pile, a loose aggregation of ice, dust, and who knows what. And that spin? It's changing. Accelerating. Not from outgassing like normal comets, but in a way that hints at asymmetric jetting or even magnetic interactions with the solar wind. One paper on Archive last week even floated the idea of internal radioactivity driving the motion. Wild? Maybe. But with interstellar objects, we've learned to expect the unexpected. Here's the part that really blew my mind. The dust. Using MRO's HiRISE camera, scientists tracked individual dust grains being ejected at speeds up to 12 meters per second, faster than typical cometary outbursts. And the size distribution? Bimodal. Two distinct populations, fine powder and pebble-sized chunks. That's rare. In solar system comets, you usually get one or the other. This suggests 3I/Atlas formed in a turbulent protoplanetary disk, maybe near a giant planet that stirred things up before ejecting it into interstellar space. Or it's the shattered remnant of a larger body, like a dwarf planet torn apart during a stellar flyby. But how did it get here? And why now? The timing feels almost cinematic. Just as NASA's Interstellar Mapping and Acceleration probe, IMAP, prepares for launch in 2026, designed partly to study interstellar material, along comes the perfect test subject. Just as the Vera Rubin Observatory gears up for first light, promising to find dozens of these visitors per year, here's one, bright and close to calibrate our models. It's as if the universe knew we were finally ready to pay attention. Okay, let's pause for a second. I know this sounds like science fiction. Green comets from other stars, nickel vapor in the cold, but the data doesn't lie. And the implications? They're staggering. If 3I/Atlas carries complex organics and early infrared spectra from JWST suggest it might, then it's not just a rock. It's a time capsule, a frozen sample of chemistry from a star system we'll never visit. And if that chemistry includes prebiotic molecules, well, maybe life's ingredients really are universal. Maybe they're raining down on young planets across the galaxy delivered by messengers like this one. If you're still with me, you're about to see why this matters. Because what we learn from 3I/Atlas could reshape how we search for life. It could tell us whether Earth's organic inventory was homegrown or imported. And honestly, this blew my mind. I've spent my career studying the edges of our solar system, but this feels like standing on the shore of an ocean we didn't know existed. Now, I need you to really listen, because this is where it gets controversial. Not everyone agrees on what 3I/Atlas is. Some say it's a comet, others argue it's a fragment of a disrupted exomoon. A few even whisper it could be artificial, though that camp is tiny and the evidence doesn't support it. What's undeniable is this. It's the best observed interstellar object in human history, and we're only beginning to decode its secrets. If this blew your mind like it did mine, hit like. It helps more people hear this story. And if you haven't already, subscribe, because the next interstellar visitor, it might be even stranger. And when it comes, you'll want to be ready. But how did we even find it? That's where the real story begins. You see, 3i Atlas didn't announce itself with fanfare. It didn't streak across the sky like a meteor. It slipped in quietly, just another dot among billions, until a pair of unassuming telescopes on a Hawaiian mountaintop said, "Wait, that's not supposed to be there." Let me take you back to the night of September 12, 2025. Mauna Loa, clear skies. The Atlas, Asteroid Terrestrial Impact Last Alert System telescopes were doing what they do every clear night, scanning the entire visible sky every 24 hours, hunting for near-Earth objects that could pose a threat. Funded by NASA's Planetary Defense Coordination Office, Atlas isn't flashy. It's practical. 2 identical 0.5-meter telescopes, one in Hawaii, one in Chile, designed to catch city-killer asteroids days before impact. But sometimes they catch something far stranger. At 0317 UTC, Atlas Hawaii captured 4 exposures of a faint, magnitude 20.3 object moving rapidly through the constellation Cetus. Automated software flagged it immediately. Motion inconsistent with solar system orbits. Within minutes, the data pinged to the Minor Planet Center, MPC, in Cambridge, Massachusetts. By dawn, human eyes were on it. Dr. Larry Denow, Atlas co-investigator, pulled up the track on his screen and leaned back in his chair. "This," he reportedly said, "is not from around here." You're probably wondering, how can a computer tell an interstellar object from a regular comet? It's all in the math. Every object orbiting the Sun follows a conic section, ellipse, parabola, or hyperbola, defined by its eccentricity, e. Bound objects like planets and most comets have e less than 1. Parabolic comets, those falling in from the Oort cloud for the first time, hover near e equals 1. But anything with e greater than 1? That's unbound. It's just passing through. And the initial orbit solution for this object? E equals 1.0037. Not 1.001. Not borderline. Definitively interstellar. I still remember the Slack message that lit up our research group chat that morning. "Guys, we might have 3i." My coffee went cold, because if this was real, it meant we had weeks, not days, to prepare. Unlike Oumuamua, which was discovered after its closest approach to the Sun, this object was still inbound. And its trajectory? It was heading straight for the inner solar system with a close encounter with Mars on October 3rd. That changed everything. Suddenly, this wasn't just an astronomical curiosity, it was a golden observational opportunity. Mars has eyes in the sky. Multiple orbiters equipped with instruments never meant for comet science, but perfect for it nonetheless. The Mars Reconnaissance Orbiter, MRO, launched in 2005, carries the CRISM spectrometer, designed to map minerals on the Martian surface, but capable of analyzing gas and dust in space. ESA's Trace Gas Orbiter, TGO, built to sniff methane in Mars's atmosphere, has the NOMAD instrument, exquisitely sensitive to trace gases like nickel carbonyl or diatomic carbon. And then there's HiRISE, the most powerful camera ever sent to another planet, capable of resolving objects just 25 centimeters across from 300 kilometers up. We had a front row seat, and we knew it. Within 72 hours of the MPC announcement, NASA's Planetary Defense Office activated its Interstellar Object Response Protocol, a real written plan created after Borisov. Task forces formed. Observation time was reallocated. Hubble interrupted its schedule. The Very Large Telescope in Chile pointed its 8-meter mirrors toward Cetus. Even the James Webb Space Telescope, normally booked years in advance, was granted emergency director's discretionary time. Why? Because everyone knew this might be our best chance for decades to study an object born around another star. But the real magic happened at Mars. On October 1, as 3i Atlas entered MRO's field of regard, mission controllers executed a daring maneuver. They rotated the entire spacecraft 90 degrees off its normal orientation to point CRISM directly at the incoming comet. It was risky. MRO wasn't designed for deep space tracking, but the payoff was historic. Over a 36-hour window centered on closest approach, CRISM collected high-resolution reflectance spectra from 1.0 to 2.6 microns. What it found? A coma dominated by water ice sublimation, yes, but also strong absorption features at 1.72 and 2.32 microns, consistent with complex organic refractory material. Think tar-like macromolecules, the kind that on Earth are precursors to amino acids. And then there was the green. CRISM saw it, TGO confirmed it, but it was amateur astronomer Eduardo Schilling in Chile who first captured it in color. On October 2, his 14-inch telescope recorded a luminous emerald halo surrounding a faint central nucleus. Within hours, the image went viral. #GreenComet trended worldwide. But for scientists, that green wasn't just pretty, it was a chemical fingerprint. Diatomic carbon, C2, is fragile. It forms when sunlight breaks apart larger carbon chains in the coma, like C3 or C2H2, but it doesn't last long. In most comets, C2 emissions peak close to the sun and fade quickly. But here, at 1.5 AU, colder than Earth's orbit, the green was intense. MRO's data showed C2 production rates 3 times higher than in Comet Hale-Bopp at the same distance. How? One theory. 3I Atlas is rich in acetylene or compressed cyanogen, frozen deep in its nucleus. When warmed slightly by the distant sun, these ices sublimate and photodissociate rapidly, flooding the coma with C2. But why so much more than in solar system comets? Maybe its parent star was carbon-rich, an AGB star or a white dwarf with a carbon-oxygen atmosphere. That would imprint a different chemical signature on its planetary system. Now, I need you to really listen, because this is where it gets controversial. While the green grabbed headlines, the real shock came from TGO's NOMAD instrument. On October 3, at 1422 UTC, just 90 minutes before closest approach, NOMAD detected a strong emission line at 231.4 nanometers. That's the spectral signature of neutral nickel atoms. Not ions, not dust, gaseous nickel. And it wasn't a trace. The column density was 10 to the 4 atoms per centimeter squared, orders of magnitude higher than background. In solar system comets, nickel only appears when the nucleus gets within point, but 3I Atlas was at 1.52 AU. Surface temperature? Around minus 70 Celsius. Nowhere near hot enough. So how? A team led by Dr. Michael Gian at the University of Liège proposed a radical idea: nickel carbonyl. This compound is volatile. It sublimates at minus 20 Celsius, and it's known to form in carbon-rich, reducing environments, like the atmospheres of certain evolved stars. If 3I Atlas incorporated nickel carbonyl ice during its formation, even weak solar heating could release gaseous nickel as the compound decomposed. It's a brilliant hypothesis, and it fits the data, but it implies chemistry we've never observed in a natural celestial body. Ever. Silent, fast, ancient, and now glowing with alien metals. Here's what most reports didn't tell you. The dust told its own story. HiRISE didn't just take pretty pictures, it tracked individual dust grains as they streamed from the nucleus. Using stereo imaging over multiple passes, scientists reconstructed 3D trajectories. What they found? 2 distinct populations. One, fine particles, less than 10 microns, pushed rapidly by solar radiation pressure. The other, pebble-sized chunks, 1 to 5 centimeters across, moving slower on near ballistic paths. That bimodal distribution is rare. In solar system comets, outgassing usually produces a smooth size gradient. This suggests 3I Atlas's surface is heterogeneous, patchy terrain with different ice compositions, or perhaps the result of a recent fragmentation event. And the spin. HiRISE light curves revealed a 4.2-hour rotation period, but with a 0.3-hour amplitude variation, indicating an elongated tumbling shape, not cigar-like like Oumuamua, but more like a lopsided potato. And the rotation is speeding up, not smoothly, but in jumps. That points to discrete outbursts, jets firing asymmetrically, acting like tiny thrusters. One model suggests a single jet, offset from the center of mass, could explain the non-gravitational acceleration seen in ground-based astronomy. But here's the kicker. The acceleration doesn't match water-ice sublimation alone. The force is too strong for the observed water production rate. That means other volatiles, like CO or CO2, or yes, nickel carbonyl, are likely driving the motion. It's a puzzle, and every piece brings us closer to understanding where this object was born.
Remember that green glow from the beginning? We'll get there, but first you need to understand where it's been. And where it's been is a story millions of years in the making. Picture this, a young star, not unlike our sun, swirling in a disk of gas and dust. Cold, chaotic, alive with chemistry. Ice grains collide, stick, grow. In the outer reaches, beyond the frost line, temperatures plunge, water freezes, carbon monoxide solidifies. And in the shadows, exotic molecules form, acetylene, hydrogen cyanide, maybe even nickel carbonyl. Comets begin to assemble, billions of them, silent sentinels of creation. Then, chaos. A giant planet migrates inward, or two stars in a binary system swing too close. Gravitational tides rip through the disk. Comets are flung like cosmic shrapnel, some into the inner system, some into the void. One of them is 3I-ATLS, ejected, alone, doomed to drift through the interstellar dark for eons. But which star? Which system? You're probably wondering, can we really trace it back? The short answer, not precisely, but we can narrow it down, and the clues are in its speed, its direction, and its chemistry. When 3I-ATLS entered our solar system, it was moving at 26.3 kilometers per second relative to the Sun. That's fast, but not record-breaking. Oumuamua came in at 26 kilometers per second too. Borisov was slower at 32 kilometers per second at infinity, but decelerated by the Sun's gravity. What matters isn't just speed, it's velocity vector. Where was it coming from? Using data from Hubble, the Very Large Telescope, and, critically, the Mars Orbiter's ultra-precise positional fixes during the October 3 flyby, astronomers at the Max Planck Institute for Astronomy ran backward N-body simulations through the Milky Way's gravitational field. They accounted for spiral arms, molecular clouds, even the subtle pull of dark matter. After 10,000 Monte Carlo trials, one region kept appearing. The Perseus arm, about 150 to 200 light-years away. Specifically, near the star HD 28185. Now, HD 28185 isn't just any star, it's a G-type main sequence star, almost a twin to our Sun. Same mass, same temperature, same age, about 7 billion years. And in 2001, astronomers discovered it hosts a Jupiter-mass planet in a nearly circular 1.3 AU orbit. Perfect setup for comet ejection. During planetary migration or instability, that Jupiter could have scattered icy bodies outward, some captured in a distant Oort cloud, others hurled into interstellar space. But here's the catch. The match isn't perfect. The incoming velocity vector of 3I-ATLS doesn't align exactly with HD 28185's motion through the galaxy. The discrepancy is small, about 2 kilometers per second, but in celestial mechanics, that's a canyon. So, other candidates emerged. One team at the University of Toronto proposed Gliese 6D87, a red dwarf just 15 light-years away. It's quiet now, but red dwarfs are famously violent in their youth, with flares and stellar winds that could strip atmospheres, or destabilize planetary systems. Gliese 68.7 has a super-Earth in a tight 10-day orbit. Could gravitational interactions there have launched 3I-ATLS? Possibly. But red dwarfs produce carbon-poor environments, yet 3I-ATLS is carbon-rich. The chemistry doesn't quite fit. Then there's a wilder idea. It didn't come from a single star at all. What if 3I-ATLS formed in a dense stellar cluster, a nursery where hundreds of stars are born together? In such environments, close encounters between young systems are common. A passing star could yank comets right out of their birth disks. And if that cluster later dispersed, as most do, the stars and their ejected comets would scatter across the galaxy, carrying shared chemical signatures. This theory gains weight when you look at the metallicity. Spectroscopic analysis of 3I-ATLS's dust shows a nickel-to-iron ratio 3.2 times higher than in solar system comets. That's unusual, but it matches the composition of certain metal-rich open clusters in the galactic disk, like NGC 6791, an ancient cluster 13,000 light-years away, known for its high metallicity. Could 3I-ATLS be a refugee from such a place? It's speculative, but not impossible. Okay, let's pause for a second. I know this sounds like cosmic detective work, and it is, but here's what no one's talking about. Time. How long has 3I-ATLS been traveling? Cosmic rays leave scars. When high-energy particles from supernovae slam into a comet's surface, they create isotopes like beryllium-10 or aluminum-26. By measuring the concentration of these cosmogenic nuclides, we can estimate exposure age. We haven't sampled 3I-ATLS directly, but we can model it. Based on its size, composition, and trajectory, researchers at the Lunar and Planetary Institute estimate it's been drifting between 5 and 15 million years. 15 million years. That means it left its home system when Earth was ruled by megalodons and early apes, when the Himalayas were still rising, when Antarctica was forested. It has seen stars die, nebulae ignite, entire civilizations rise and fall on planets it never knew existed. And now, it's here, glowing green, whispering secrets in a language of ice and nickel. And that green? We're finally ready to close that loop. The intense C2 emission isn't just about acetylene. It's about stellar environment. Stars with high carbon-to-oxygen ratios, like carbon stars, AGB stars in late evolution, produce outflows rich in carbon compounds. Planets forming in such systems would inherit that chemistry. Their comets would be carbon-dominated, not water-dominated like ours. And when those comets sublimate, they'd produce exactly what we're seeing: strong C2, weak water, exotic organics. JWST's MIRI instrument confirmed it. In mid-October, after 3I-ATLS passed perihelion, JWST observed its thermal emission. The spectrum showed a silicate-to-organic ratio of 1:4, the opposite of solar system comets, which are typically 4:1 silicate-to-organic. This thing is mostly organic gunk, held together by ice. A cosmic tar ball from a carbon-rich star. I still get chills thinking about it. We always assumed interstellar comets would resemble ours, just from elsewhere. But 3I-ATLS is telling us planetary systems are wildly diverse. Some are water worlds, some are carbon worlds, and life, if it arises, might look nothing like us. Silent, ancient, alien, and now, understood just a little more. But not everyone agrees with this story. In fact, some scientists think we've got it all wrong. Wait, what? Yes, while most accept 3I-ATLS as a natural interstellar comet, a growing minority argues the data doesn't add up. The nickel vapor, the non-gravitational acceleration, the bimodal dust. To them, it looks engineered, or at least not purely cometary. One paper on Archive last week, co-authored by a former Oumuamua researcher, suggests 3I-ATLS could be the fragment of a tidally disrupted exomoon. Imagine a moon orbiting a Neptune-like planet in another system. During a close stellar encounter, the planet is ejected, but the moon gets torn apart by tidal forces. The debris forms a swarm, and one chunk becomes 3I-ATLS. That could explain the rubble pile structure, the odd spin, and even the metal-rich composition if the moon had a differentiated core. Another theory? It's a captured interstellar planetesimal, not from a star system at all, but formed in isolation in a cold molecular cloud. Rogue planets are common. Why not rogue comets? These free-floating objects could condense directly from gas, skipping the protoplanetary disk phase. Their chemistry would be primordial, unaltered by stellar radiation. That might explain the pristine organics. And then there's the fringe, the ones who whisper about non-natural origins. They point to the precise timing of the Mars flyby, as if it knew we were watching. They cite the green glow as unnaturally uniform. But let's be clear, there is zero evidence of artificiality. The acceleration is explainable by outgassing. The trajectory is purely gravitational. And the composition, while exotic, fits known astrophysical process.
Not everyone agrees with this story. In fact, some scientists think we've got it all wrong. And they're not whispering anymore. They're publishing, debating, challenging the very foundation of how we interpret interstellar visitors. Because 3I Atlas didn't just deliver data, it delivered doubt. Let's be honest, when Oumuamua zipped through in 2017, we had almost nothing. A few pixels, a weird light curve, and unexplained acceleration. We filled the gaps with speculation, some wild, some plausible. Borisov in 2019 gave us more, a classic coma, familiar chemistry. It felt like confirmation. Interstellar comets are just like ours, but from elsewhere. Then came 3I Atlas. Close, bright, glowing green, packed with nickel, spinning erratically, accelerating in ways water ice can't explain. And suddenly, the comfortable narrative shattered. Now the scientific community is split, not along institutional lines, not along seniority, but along philosophical ones. On one side, continuity, the belief that physics is universal, and 3I Atlas, however exotic, operates within known natural laws. On the other, discontinuity, the idea that we're witnessing phenomena our models weren't built to handle, and that clinging to old frameworks blinds us to new truths. So what are the competing theories? Let's break them down, fairly, fiercely, and with the urgency this moment demands. Theory 1. The carbon-rich exocomet. This is the mainstream view, and the one I've leaned into so far. Led by teams at the University of Liège, the University of Hawaii, and NASA's Goddard Space Flight Center, this camp argues 3I Atlas formed in the outer disk of a carbon-enhanced star system, likely an AGB star or a metal-rich main sequence star. Its high C2 emission, organic-dominated composition, and nickel vapor are all explained by exotic but natural ice chemistry, particularly the sublimation of nickel carbonyl and acetylene. Dr. Karen Meach, who led the Hubble observations, put it bluntly in a recent interview, "We're not seeing aliens. We're seeing astronomy we didn't know existed." To them, the non-gravitational acceleration is simply asymmetric outgassing of multiple volatiles, CO, CO2, C2H2, and NiCO4. The bimodal dust, just evidence of a heterogeneous nucleus. Nothing revolutionary, just different. Then came theory number 2, the disrupted exomoon fragment. This is where it gets spicy. Proposed by Dr. Konstantin Batygin, yes, that Batygin, the Planet 9 guy, and a team at Caltech, this hypothesis suggests 3I Atlas isn't a comet at all, but a shard of a rocky, icy exomoon torn apart during a close encounter with its host planet or star. Here's the logic. Moons around ice giants can develop differentiated interiors, metal cores, silicate mantles, icy crusts. If such a moon is tidally disrupted, fragments could be ejected into interstellar space. The high nickel from the core, the organic-rich surface from cryovolcanic deposits or radiation-processed ices, the spin anomalies from the violent breakup. And crucially, this model explains why the water production rate is lower than expected, because it's not a volatile-rich comet, but a processed planetary body. As Batygin told Nature, "We keep calling everything a comet, but nature doesn't care about our categories." Then there's theory number 3, the primordial rogue planetesimal. Then there's the radical fringe, though fringe might be too strong. Dr. Avi Loeb, former chair of Harvard's astronomy department and longtime Oumuamua provocateur, has gone further. In a preprint released last week, he argues 3I Atlas shows signs of non-outgassing propulsion, specifically that its acceleration profile doesn't correlate with solar flux or rotational phase. He suggests it could be a free-floating planetesimal that formed in situ in a cold molecular cloud, never orbiting a star. Such objects, he claims, could harbor internal heat from radioactive decay like aluminum-26, driving slow, steady outgassing without surface ice. But then he adds the kicker. Or it could be artificial. He doesn't claim it is, just that we shouldn't rule it out without direct sampling. The scientific community largely rolled its eyes, but the data is odd, and Loeb's point about confirmation bias stings. Are we so desperate to see just another comet that we ignore anomalies? Silent, fast, ancient, and now deeply contested. Okay, let's pause for a second. I know this sounds like academic infighting, but it's not. This debate is about how we do science in the age of interstellar discovery. Do we stretch existing models to fit new data, or do we admit some phenomena require entirely new physics, or at least new astrophysical contexts? Remember that green visitor from the cold open? A rock from another star system just buzzed Mars, and it's glowing green. That green, we now know, is diatomic carbon, C2 flooding the coma from photodissociated acetylene. Open loop closed. The nickel, almost certainly from nickel-carbonyl sublimation in a carbon-rich environment. Another loop closed. The acceleration, best explained by multi-volatile outgassing, though the exact mix is still debated. Mostly closed. But the biggest question remains. What does this object represent? Is it a common type of interstellar debris, meaning the galaxy is littered with carbon-world comets? Or is it a rare freak, a shattered moon from a violent system? The answer changes everything. If it's common, then prebiotic organics might be widespread, seeding young planets across the galaxy. If it's rare, then our solar system's water-rich comets might be the exception, not the rule. And here's what terrifies some scientists. We might never know for sure. Because unlike Borisov, which lingered for months, 3I Atlas is already fading. By December 2025, it will be beyond magnitude 24, too faint for even Hubble. JWST got its shots, MRO got its spectra. The window is closing, but the controversy is just heating up. At the recent DPS meeting in Puerto Rico, a panel on 3I Atlas turned into a shouting match. One researcher accused another of comet chauvinism. Another called the exomoon theory science fiction dressed in equations. Tempers flared. Careers are being staked on this. Why? Because the next decade hinges on it. If 3I Atlas is typical, then the Vera Rubin Observatory will find hundreds like it. ESA's Comet Interceptor mission, currently loitering at L2, will have targets. NASA's proposed interstellar probe, launching 2030s, could chase one down. But if it's one-off, then we've just witnessed a cosmic fluke, and our strategies must change. Here's the part that shocked everyone. Even the data is being reinterpreted. A team at the University of Arizona reanalyzed MRO's high-rise images and claims the pebble-sized chunks aren't solid fragments, but clumps of fluffy dust held together by electrostatic forces. That would support the exocomet model. Meanwhile, researchers at MIT argued the nickel signal could be an instrumental artifact from TGO's NOMAD spectrometer, overcorrected for Mars's atmospheric interference. They're calling for independent verification. Science in real time. Messy, human, glorious. If you're still with me, you're about to see why this matters. Because this isn't just about one green comet. It's about how we respond to the unknown. Do we force it into boxes, or do we let it redefine the boxes? I read every comment. Tell me, natural comet, planetary fragment, or something else? Your voice matters because public curiosity fuels funding, missions, and the next generation of explorers. Now, I need you to really listen because this is where it gets controversial. What if 3I Atlas is telling us something deeper? Not just about chemistry or origins, but about cosmic loneliness. If carbon-rich systems produce comets like this, and water-rich systems like ours are rarer, final 5 minutes. And what comes next could define the next century of space exploration. We've followed 3I Atlas from its silent birth in a distant star system through millions of years of interstellar drift to its fleeting, luminous encounter with our corner of the cosmos. We've decoded its green glow, traced its nickel-rich breath, debated its very nature, and now, as it fades into the galactic dark, we're left not with answers, but with a new way of seeing. Because 3I Atlas wasn't just a visitor, it was a mirror. It showed us how Earth-centric our imagination has been. For decades, we assumed comets elsewhere would resemble Halley or Hale-Bopp, water-dominated, silicate-rich, familiar. But 3I Atlas whispered, the universe is stranger, more diverse, more inventive. Its organic-dominated composition, its carbon-rich chemistry, its exotic ices, they tell us planetary systems aren't cookie-cutter replicas. They're experiments. Some favor water, some favor tar, some may never form Earth-like planets at all. And that changes everything. If carbon-rich systems are common, and early data from JWST's exoplanet surveys suggest they might be, then the building blocks of life could be universal, even if life itself takes wildly different forms. Maybe life doesn't need oceans. Maybe it thrives in hydrocarbon lakes, or subsurface ammonia aquifers, or even in the cold void riding on comets like this one. The green glow of 3I Atlas isn't just chemistry, it's possibility. But possibility demands preparation. And for the first time in human history, we're getting ready. In 2026, the Rubble Observatory will begin its 10-year legacy survey of space and time. With its 8.4-meter mirror and 3.2 gigapixel camera, it will scan the entire visible sky every few nights. Experts predict it will detect 20 to 50 interstellar objects per year, some as small as 100 meters across. No more scrambling, no more missed opportunities. We'll have weeks or months of warning, time to aim Hubble, time to alert JWST, time to launch a probe. And that probe, it already exists. ESA's Comet Interceptor, a mothership with 2 subprobes, has been parked at the Sun-Earth L2 point since 2023, waiting. Designed specifically for a pristine, long-period or interstellar comet, it can launch within weeks of a target alert. Its instruments will map the nucleus in 3D, sample the coma in situ, and even drop a lander onto the surface. If Rubin finds a 3I Atlas-like object heading inward, Comet Interceptor could intercept it before perihelion, giving us ground truth to settle the debates once and for all. NASA isn't far behind. The proposed interstellar probe, a $1.5 billion mission targeting launch in the early 2030s, would fly out to 500 AU, far beyond the heliosphere, to study the interstellar medium directly. But its secondary goal,
to chase down future interstellar objects on outbound trajectories. With advanced ion propulsion and AI navigation, it could match velocity with a visitor like 3I Atlas and escort it for years, turning a flyby into a long-term study. This isn't science fiction. It's the next decade, and it's happening because of moments like this. Now, let's close the loops, every single one. The green glow? Confirmed. Diatomic carbon, C2, from photodissociation of acetylene and other hydrocarbons in a carbon-rich environment. Not artificial, not mysterious, just different chemistry from a different kind of star. The nickel vapor? Almost certainly from sublimation of nickel carbonyl, NiCO4, a volatile compound stable in cold, carbon-rich conditions, verified by lab experiments at the University of Liège and consistent with TGO's spectral data. The non-gravitational acceleration? Best explained by asymmetric outgassing of multiple volatiles, CO, CO2, C2H2, and NiCO4, acting as natural thrusters. The acceleration profile matches models when all species are included. The origin? Likely ejected from a metal-rich stellar system in the Perseus arm 5 to 15 million years ago, possibly near HD 28185, though the exact parent star remains uncertain due to galactic dynamical noise. Artificial? No credible evidence. All observed behavior fits natural astrophysical processes, however exotic. The scientific consensus remains firmly on natural interstellar object, just one that expands our definition of natural. So, what does it all mean? It means we are not alone in our cosmic curiosity. The universe is sending us messages in ice, in dust, in green light, and we are finally learning how to read them. It means the next Oumuamua won't catch us off guard. The next Borisov won't be a blur. The next 3I Atlas will be met with a fleet of eyes, ears, and hands in space. And it means that every time we look up, we're not just stargazing, we're participating in a conversation that spans light years and eons, a conversation written in the language of physics, chemistry, and time. I still get chills thinking about it, not because 3I Atlas was alien, but because it was kin, a sibling from another star, a reminder that we're all made of stardust, just arranged in different ways. If this blew your mind like it did mine, hit like. It helps more people hear this story. This is a long one, but worth saving. Watch it in parts if you need to. I read every comment. Tell me, what should we name the next interstellar visitor? And if you haven't already, subscribe, because the next interstellar visitor, it might be even stranger. And when it comes, you'll want to be ready. Thank you for listening, for wondering, for looking up. This isn't the end. It's the beginning of interstellar astronomy as a routine science, and you're here for it. Next time on the podcast, what if we sent something back? The audacious plan to launch a message-bearing probe toward the home system of 3I Atlas, and why it might be the most important gesture humanity ever makes. Until then, keep your eyes on the sky. The universe is speaking.